Okay. Okay, so now we're going to go on to something completely different, or somewhat different, and that is the notion of arc length. So arc length. So somebody gives you a curve like this, and they say, how long is it? Okay, what's the length? So you have a smooth function, a smooth, and what that means is that the derivative is continuous. Okay, a smooth function. Okay, and from A to B. Okay, so f of x, f goes from A to A comma B into R. Okay, and here's the graph. Here's the graph of f. Okay. Graph of f, and we'd like to know the length of the graph. Okay, how long is that curve? Okay, and as usual, the answer is I don't know, right? I don't know, but I do know how to do something simpler, right? So I do know how to do something simpler, which is I do know how to take the length between, if it's a straight line, right? If it's a straight line, then I know how to do it, right? If this is x1 and this is x2, right? If I go like this, f of x1, f of x2, right? What's the length of this straight line? What's the length of this line segment? You know it, right? The square root of the difference of the y values, right? Square minus the difference of the x values, square, right? That's the distance. Okay. So if it were a straight line, then we know how to do it. Okay. So that's something any child can do. And as usual, calculus means you take your childhood knowledge and then you combine it with limit. Combine it with the notion of limit. Okay. So you say, okay, I don't know how to find the length here, but what I'm going to do is I'm going to break this up into a bunch of subintervals. Okay. So I'm going to call these guys x0, x1, x2, x3, blah, 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 up to xn, right? And then I'm going to pretend that my function is just a bunch of straight lines. Okay? I'm going to pretend that my function is just a bunch of straight lines. Okay? And so the length, the total length, is then will be the sum of the square root of, as k goes from 1 to n, of xk minus xk minus 1 quantity squared plus f of xk minus f of xk minus 1 quantity squared. Yeah, Wang Di. Can I change my pen? This is the best pen, I'm afraid. The only pen I got left is this blue one. Okay, maybe the blue one will do it. Tyler has an extra pen. Do you have an extra pen? No, he doesn't. Okay. Okay. Can you read this one thing? You cannot. I read it again. So it's going to be the sum. This pen is not much better. Of the square root of xk minus 1 plus xk minus xk, sorry, quantity squared, plus f of xk minus 1, f of xk minus f of xk minus 1 quantity squared. This pen is not any better.
And that is the length of that.
That is what?
The length of that.
So each of those things is one of these lengths, right? Right? So from k equals 1 to n. Okay. Right? So each of the terms in the sum is going to give you the length of one of these segments. So you get the first segment plus the second segment's length plus the third segment's length plus the fourth, et cetera, and you add them all together and it gives you some approximation of the length. Okay. And then you take the limit. Take the limit. Right? Take the limit as n goes to infinity of the sum k equals 1 to n xk minus 1 squared plus f of xk minus f of xk minus 1 quantity squared, everything to that. Okay. Okay. And what we're going to do is do something funny. We're going to divide everything by delta x, and we'll multiply also by delta x. Okay, where delta x, remember delta x is the distance, right? Delta x is the length of one of these, is the difference between any two subsequent guys. Right? In fact, each of these guys is delta x, right? xk minus 1, that's a delta x right there. Okay. Putting it together, you get the limit as n goes to infinity of 1, right? Sorry, the square root of 1, right? Because this thing here is a delta x squared, right? When we move the delta x inside the square root, we get a delta x squared on the bottom, right? So that becomes 1. And here we end up with plus fxk minus fxk minus 1 quantity squared over delta x squared. Everything dx, delta x. Do you all see that? Right? This thing here, right? Notice that xk minus 1 is delta x, right? So what I have here, like what this thing is summation the square root of delta x squared plus f of x minus k minus f of xk minus 1 quantity squared. Everything over delta x times delta x. Right? I'm gonna take this delta x on the bottom and I change it into the square root of delta x squared. Right? And then put everything under the same radical. Right? Put everything under the same square root sign, and you end up with 1 plus this. Anybody confused? Anybody confused by what we're doing so far? Okay. Then what is this thing? As n goes to infinity, what do we get here? As n goes to infinity, what's this thing here, for example? Anybody recognize it? It is the maybe if I read it like this, it'll be better. Delta x, x of k minus x of k minus 1 quantity squared. Right? As n goes to infinity, what am I going to get here? What does this remind you of? Where does the 1 come from? The 1 is because we have delta x squared over delta x squared plus f of xk minus f of xk minus 1 squared over delta x squared. Right, so you got 1 plus this thing. Okay, but does anyone recognize this? I sure hope so. It's the derivative, right? So when you take the limit, what do you get? You're gonna get this is the Riemann sum for an integral, right? So you get the integral from a to b of the square root of 1 plus f prime x dx. The integral from a to b of the square root of 1 plus f prime x dx. Okay. And that is the arc length of f, the graph of f, over AB. Okay, everyone see how that happens, right? We're trying to find the length of this curve here. It's hard to do, so we take approximations, and then we take our approximations, and then let the approximations become infinitely fine, and out pops this integral. Okay, out pops this integral. That's what we're going to take to be the length of the curve. Okay, so let's do an example. So suppose somebody says, I'd like to know, my function is going to be f of x is x squared. Okay, here it is, it's your parabola, right? Right? And suppose you want to know the length from 0 to 1. Okay, so you just want to know the length what's the length of this curve here? Okay. So you say, okay, well, what I need to do is take the integral from 0 to 1 of the square root of 1 plus f prime x, squared. Right. 1 plus, right, f prime x squared, right? Well, f prime x is, of course, 2x, so we get 4x squared dx. Okay. So then you evaluate that integral. You probably have to use a trigonometric substitution, right? Right. You take 2x, right? Let 2x be tangent beta. Right, and then you do your trigonometric substitution, you get some number, and that'll be the length of the parabola, of that part of the parabola. Okay. Okay. Similarly. Similarly, if we take, right, if g is a function of y, if g is a function of y, right, so you have some function of y like this, right, between y equals c and y equals d, right. Then you can also get the length. The length is, of course, going to be the integral from c to d of the square root of 1 plus d prime y squared dy. Right. So you can do it in x and you can do it in y. That's obviously. Longby, can you see? The length equals the integral from c to d of the square root of 1 plus g prime y squared dy. Let me have you do an exercise. Okay. So exercise y equals x cubed over 3 plus 1 over 4x from x equals 1 to x equals 3. So somebody gives you this, this equation, and says, tell me how long this part of the graph of the equation is. so what is it? Please talk to somebody. Okay, please talk to somebody nearby. It's easy, right? What's the answer? I mean, what's the integral? Who can tell me the integral? Won't how about you?
I actually, I'm not sure the integral could be x squared plus minus 1/4 x cubed.
Say it again, please.
X squared
X squared
minus 1/4 x cubed.
minus 1/4 x cubed. So you need to differentiate this, right? So you get, x squared. This is 1/4 of x to the negative 1, right? So you're going to get minus 1/4 x to the negative 2. Okay. So you get,
Is that?
That's a 4.
X squared.
This is an x.
X squared.
Yeah, so you
Oh, I thought that is x
oh no, this is 1/4x.
squared.
Okay. So you end up with this as the derivative, right? Okay.
Yes.
And then you say, okay, so I'm going to get the integral from 1 to 3 of the square root of 1 plus that thing squared, right? So this minus 1/4x minus 2 squared. Okay, whatever that turns out to be. It's kind of awful. Anyway, that's the integral that you need to evaluate. Okay. Is that clear? Okay. Okay, let me show you one last thing about arc length. What we showed before, these first two things are how to find the arc length of the graph of a function. Okay, but sometimes you might not have the graph of a function, but you might have some sort of parametrized curve. Okay, so arc length for parametrized curves. Parametrized curves. Okay, so you could have something like this, given a parametrized curve that looks like x of t y of t when t ranges over some interval. Okay. So I'm not sure if you've seen this sort of thing before. How many of you have seen parametrized curves before? Anybody seen parametrized curves before? So for example, if I have cosine t, sine t, and t goes from, say, 0 to pi over 2. Okay. Then this is a description of a curve, right? This is a curve in R2, right? At time 0, you're going to get cosine 0, sine 0, right? That's 1 comma 0. And then as t goes from 0 to pi over 2, the point is going to walk on the circle, right? It's going to walk on the circle in this direction, right? And so this thing is a parametrization of this curve. Okay. If I went, say, from here to 2 pi, right? Then I'd have a parametrization of the whole circle, right? Okay, so this is an example of what's called a parametrized curve. Okay. If I were in 3 dimensions, say, and I had cosine t, sine t, t, right, x, y, z, then what that would be is something that looks like a circle from the top, right? It would be something like this, right? If you ignore the z variable, it's just a circle going round and round, right? Looking from the top, it's just a circle going round and round. But as t increases, the height increases. Okay, and so this would be a parametrization of this helix. Okay, here's examples of parametrized curves. And so maybe somebody says, I'm going to give you a parametrized curve. How do you figure out the length of it? So again, how to find arc length. Okay, so somebody gives you this parametrized curve. Here it is, right? And says, find me the arc length of this thing. Okay. So, right. So from A as t ranges from A to B, x of t, y of t, walks around. This is x of A, y of A. This is x of B, y of B. Right? And as t increases, then this thing walks along the path and then ends up here. Right? And you're wondering how long that curve is. Okay. And as usual, you play the same game. You say, we play the same game. Okay. You take approximations. You say, okay, chop up the t world, right? Chop up your time interval into even pieces, right? T0, T1, Tn, right? And then the approximation is going to be summation, x of tk minus x of tk minus 1, quantity squared, plus y of tk minus y of tk minus 1, quantity squared, everything to the square root. That's k ranges from 1 to n. Okay, so same idea as before. Right, same idea as before. Okay, and then you take the limit and realize that this is a Riemann sum. You play the Riemann sum game and take the limit, and you end up getting that the arc length is going to be the integral from a to b of x prime squared plus y prime squared quantity to the half dt. So you do exactly the same thing. We divide by, divide by delta t, multiply by delta t, and do the same thing as we did before. Okay. Let's do a simple example. Simple example is x is cosine t, y is sine t. We already know a lot about this one. Okay, so let's do the thing we were looking at earlier, right? What's the length of this? You already know the length of this, right? It's pi over 2. Right, but let's calculate it, right? So you say, okay, the arc length is going to be the integral from 0 to pi over 2, right? So t ranges from 0 to pi over 2. The arc length is going to be the integral from 0 to pi over 2 of the square root of x prime squared plus y prime squared. Right? But x prime squared is negative sine quantity squared, so that's sine squared. And y prime squared is cosine squared. And you know that that sine squared plus cosine squared is 1. Right? So this is going to be integral from 0 to pi over 2 of 1. That's just going to be pi over 2. Okay. Another example. Everyone okay? First, is everyone okay with the example? Any questions on the example? Right? Just take x prime squared plus y prime squared. Right? Sum down, take the square root. Okay. So there's another one. X equals cosine cube t. Y equals sine cube t. As t ranges from 0 to pi over 2. Okay. This ends up looking something like this, I think. Okay. But again, you just follow the rules, right? You just say, okay, this is going to be the integral from 0 to pi over 2 of, right, x prime, right? So x prime is 3 cosine squared t negative sine t, right? Y prime t is 3 sine squared t cosine t, right? So then you go, the square root of that squared plus that squared. Right, so 9 cosine 4 sine squared, cosine 4t sine squared t, plus 9 sine to the fourth t cosine squared t, quantity dt. So in any case, this sort of thing, you see how to do it, right? Define, somebody gives you a parametrization, And then, to find the arc length, you just, take the integral of this thing here.